I do it in lab, just like this one. All right, so we're gonna have some fun today. Okay, so there are, um, so I'm gonna go ahead and start. Normally, I would do this on maybe on Thursday, but I want to go over Lab 7 today, just simply because well, I was hoping more people would be here, but maybe they'll join online. It's good that I started uh, everything a bit later. Um, Let me go ahead and share my screen. Okay, so hopefully it wasn't too bad getting here today. I did have to I did have to plan out a couple different routes, so it was a bit of a, uh, um, I understand if basically you are missed class and you're watching this later. So let's go to data structures. And this is one of my favorites because the problems here are fun. Okay. Or at least they're good puzzles, right? I guess it's hard to figure out what people find fun, but these problems, index tree, recursion, are fun problems. Now, I will double check the due dates, because I expect you to work as much over the break as I do, which is not very much, because it is a break. If you're very behind, obviously you want to catch up, but it is obviously a chance to refill your batteries, so to speak. All right. So I will say this. Both of these problems are like super online. Like, don't even bother using AI. You can find humans who have written this. This was homework back when my CS professors were taking this stuff as students. Okay, so these problems are like so well known. So you can look these up. You could. I'm not giving you permission to. I'm saying you could totally, in theory, look these up, and I urge you not to, not for the reason of, well, that's academically dishonest and, and all that standard jazz about being in trouble, but because these are such interesting problems and you'd be robbing yourself of the opportunity to solve them yourself. You'd be robbing yourself of the learning experience of something that's actually really interesting. Okay. Each of these are worth 75 points. You have the choice, once again, you have the choice of doing 2 for the first problem. So 1 of 2. And then you also have to do Sudoku. So if you do not know how to play chess, that is fine. Basically, we're just asking in that case, just do the first of the 2 chess problems, because that's just simply asking how can we place 8 pieces on a grid such that none of them we can draw straight, so such that we can't draw a straight line to any of them, any pair. So you'll be learning recursion. Now, my videos assume that you have no idea what recursion is, right? Even though you have totally learned recursion at some point, right? In 1068, I believe Professor Fiore goes over recursion, right? So I assume that you have no idea what recursion is, but we really get into it here. And there's a number of different strategies you can use with recursion. And one of them is backtracking with recursion. So essentially what we did with the chess problem, only we're just going to be using a stack implicitly rather than explicitly. You see, there are very, very, very few things, and possibly nothing, that that can only be just written with recursion. In fact, partially because the recursion uses a runtime stack. It uses a stack of memory to figure out where the method calls were. I hopefully go into this in more of my videos. But anyway, the overall algorithm for backtracking is, assume we want to solve something and we've got a board set up for some kind of puzzle, any kind of puzzle. What we're going to do is that this is a recursive problem, and we pass in the board as we currently have it solved. So the current state of the board. So that's going to usually be a 2D array in these puzzles, a 2D array of ints. And we give our position. Now, depending on the puzzle, that can be a row, it could be a column, or it could be a row and column, right? It could be 1 or 2 variables. But regardless, It's just simply where we currently are in the puzzle. The goal of this strategy is we have giant big puzzle over here, which is very hard to solve. So let's make it easy for ourselves. And rather than trying to solve this giant puzzle all at once, we're just going to look at this position and try to solve only this position and leave it as an exercise to future us or future calls of the program to try to solve the rest of the puzzle. We assume that everything else in the board has been solved correctly, and we just try to solve our current position as best we can. So what we do is that we have the first thing called a base case. And a base case is basically, if you remember my proof by induction that I did, it is essentially the simplest problem. So if you have an infinite series, it is basically setting up, oh, the two sides of the equation, here's what it's like when n equals 1, the most simple thing. So here, if position is such, there's nothing left to solve in the puzzle, return true. So in other words, something like we are out of pieces, or we went out of bounds because we just finished solving all the rows and columns. That's us saying we're done. So we'll return true. In this case, true will indicate that we successfully solved the puzzle, and false will indicate we've hit a dead end. We've hit an impossible configuration and we need to fix something. Okay? So if we're done with the puzzle, return true. The next clause is what we call our figuring out what our recursive case is. So for each possible choice that we can make at that position, we check if that choice is valid. Believe it or not, this is the hardest part of the puzzle, even though what seems to be hardest comes next. Okay. What we do is that we check if this is valid. In other words, if this is okay for us to try to solve this. My recommendation for all these puzzles is when you write your valid function, you just set it to be return true at first. Everything is valid, sure. But that will let you check that the rest of this program works, that the recursion works, that it all magically comes together. Okay, and then you can go through all the different checks you need to do to check that it's valid. So just in the beginning, just set that, set your valid function to be a Boolean function that returns true. Okay, so if that area is valid, then what we do is we say, hey, mark the board at position with the choice. So that might be writing down the number on Sudoku or putting a piece down at that row column in chess. So we mark it. And then here is the part that is theoretically the most complicated, but once you get used to it, super easy. If solve board position plus 1 equals true. So we have a method call inside an if statement. We could always bring that out, but honestly, it just makes sense to put it in here. So what we're doing here is that we are recursively calling solve. Solve calls solve board plus 1. Now, normally, in intro to programming, we basically say, don't make a method call itself. It will go on forever. Here, though, we're kind of guaranteeing that's not going to go on forever because the solve method at position will call position plus 1, which that one, when it runs, will call position plus 2, which will call position plus 3, which will call position plus 4. And eventually, you'll get it to such that there's nothing left to solve, so you'll return true, which will make this return true, and if this gets true back, we return true. And so that just basically becomes a cascading call of true statements. Basically, what we're saying is, I'm lazy. I'm just going to solve what I can at my personal square, and then I'm going to do a method call, a magic method call that solves the rest of the puzzle, continuing on from here. That just happens to be the method that I'm currently running. If, however, you get false back, then we don't return true. That was bad. That's a dead end. This is a non-viable condition. So we will remove any marking we made and continue going through all our choices, all of our remaining choices. If we go through all our choices and we can't solve anything, if for some other reason you aren't able to unmark your squares, you're going to do that here. unmark that square position. You do that here, and we return false. So that's where our return false is. And the return false basically is sent back to a solve call that says, hey, you led us to a dead end. You need to change whatever choice you made. So the two problems are 8 queens, and I have a good I have a physical chessboard in one of my videos where I go through this and solve it by hand. So I'm not going to go over it other than to define what this problem is. By the way, getting this grid here was actually one line of code in LaTeX for me to do. So that was pretty cool. Import package, write a line of code, get chessboard out. So the 8 queens problem is a very well-known problem. It basically says, hey, we've got this problem. We've got this piece in chess called the queen. The queen is the most powerful piece. It can attack. It can move an unlimited number of spaces in any direction, in any of the cardinal directions. So north, south, east, west, and on the diagonal. So it's a very powerful piece. A chessboard has 8 rows and columns. The 8 queens puzzle is, can you place 8 queens on a chessboard in such a way that no queen could capture the other? So none of these queens share a row, a column, or diagonal. Okay. So my hint to you here is only one queen can be placed on each column. So your position in the puzzle should probably be what row you're on, what column you're currently in. And your choice is, what row am I going to put the queen in? So that's how you translate that one. If you're up for something a bit more challenging, you can try something called the Knight's Tour. Here is a knight. It moves in a weird L shape. As displayed here, two squares in one direction, in one axis, and one square in another axis. Okay. And the goal here is you can start your knight anywhere you like on the board, and the goal of the knight is to travel the entire chessboard, visiting each space only once. So a bit more difficult, but mainly because you have to do out of bounds checks. All right, and finally, Sudoku, which I'll go over here, because I don't really describe what a Sudoku puzzle is. Write a program that can solve a Sudoku pit puzzle. And I see a lot of people misspelled it. It says Sodoku. It's Sudoku. It's Japanese. It's there's a number of languages that really like their abbreviations, and Japanese loves them. Is one of those. You know, personal computer becomes Pasokan instead. So Sudoku is its own. I'll pull up a puzzle so we can show you. But Sudoku becomes its own thing. It is literally number place, but it is a etymology. Where is that etymology? Come on. Literally single digit. No, where's the origin? Come on, there's more Japanese in there. There we go. It is short for Suji wa Dokushin na Kagiru. So Suji wa Dokushin ni Kagiru. Okay. The digits must be single. The goal is you get a puzzle that looks like this. Okay. This is considered to be a very easy Sudoku puzzle. It's a 9x9 grid, so represented as an array of integers. Okay. And the goal is that you want to fill out this board, every row and column. And as you notice, this 9x9 is split up into little 3x3 squares, right? Right. So like you've got the top left, you've got the center, you've got the top right, you've got the middle. So each row, each column, and each of these 3x3 squares can hold each number 1 through 9 exactly once. So if we look at a solution, notice that this row only has that one appears only over here. In this column, It appears once in this row and once in this 3 by 3. Okay. So these things are pretty, they're pretty nifty to solve. Some of them, the more advanced ones, do require a bit of guessing and then backtracking on it. There are some variations for like doing jigsaw kind of ones, which are interesting. But so there's plenty of variations. But what we want to do is we want to write a problem that solves these Sudoku puzzles. And these aren't too bad to solve. For instance, we know that as humans, we'll use a lot of logic. Over here, we have an 8 in this in this column, an 8 in this second column. That means we haven't put an 8 in this column. Now, here's the interesting thing, though. We can figure out where 8 is supposed to go in this column because we know there's an 8 in this 3 by 3. There's an 8 in this 3 by 3. So we know that the 8 can't be here. It can't be in any of these 3. So 8 either has to be in this, is somewhere in this bottom square, either here or here, but it can't be here because there's an 8 in this row. So we know that the 8 needs to go here. Make sense? And then you just kind of follow that logic. Can we knock out any other of the 8s? Well, we don't have an 8 in this row over here, but we have an 8. We don't have an 8 in this row over here. So it can't go here. It can't go here. Can't go here. Can't go here because of this. And it can't go here. So the 8 has to go here. Right? So you can get a lot of logic out of these things. You can solve a lot of these with logic and not guesswork, but some of these do require some guesswork and backtracking. Now, Sudoku is especially interesting because it's just 9 by 9, so your computer can easily solve it. But it's actually in a class of problems we classify as NP-complete problems, non-deterministic polynomial complete, which means that actually, if we were to consider an n by n problem, it belongs to, an n by n Sudoku grid. So maybe like a 20 by 20, right? We can abstract this out. Okay. Maybe 25 by 25 would be easier since it's squared to easier. But the point being is that we abstract this out. This problem becomes a class of problems that is some of the hardest problems we know we know about. And they all basically have a runtime currently that looks like this or like this. Bad runtimes. And this one, your computer can solve this because this is a very small space. But turns out these problems are really hard and they're frustratingly common. Problems like traveling salesperson problem, doing some level generation kind of stuff, protein folding, doing some stuff related to primes. So a lot of these problems are frustratingly difficult. But in short, what these means is that these are a class of problems that are extremely difficult to solve, but once you're given an answer, like we have over here, it's easy to verify that we have a correct answer. You learn more about this in algorithms, but I have a video linked in a playlist called Videos Worth Watching, which goes over these kind of things, and it's exceptionally interesting because one of the ways we can prove that problem is NP complete is we take our unknown problem that we're trying to figure out, and we transform a NP complete problem into this problem, into the problem we're trying to show what the runtime is. And that shows that problem is NP complete because it's not really too exciting to transform any problem into NP complete because we're humans. We're masters at making stuff more difficult than it needs to be. So turning it into a hard problem is not a very fancy trick. But taking a hard problem and transforming it into this problem, that basically says if we had a magic method to solve this new problem, then we could solve the NP complete problems in very fast time. So how do we go about solving Sudoku? Well, let's see the algorithm in action, right? And we're going to go with easy because it's hilarious. But we're going to do a kind of terrible algorithm here, our recursive backtracking algorithm rather than doing logic. Basically, we're going to start at the top left. And we'll have another clause that basically, a very easy recursive case, which is that if our position is already filled, we are just going to recursively call the next position. So what do we do? Well, given our position, we try each choice in this position. So is 1 valid? No. Is 2? Yes. Move on to the next one. Is 1? No. Is 2? No. Is 3? No. Is 4? 5? 5 is valid. 1, 2. Oh, 1 works. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 works. And then we will go all the way up to 8. Does 8 work? Yes, it does. Move on to our column is equal to 9, so we'll set it equal to 0 and increment the row. 1, 9, 7. Okay, 1, 2, 3, 2. 1, 2, 3, 4, 4. 1, 2, 3, 4, 5. 1, 2. Told you it's silly. This does not work for all the puzzles. Notice that here, what happened? I went through all the choices, none of them exist, so I have to backtrack. So what does that mean? Go back to here, said you led us astray, you led us to a dead end. Backtrack. Seven, 8, 9, backtrack. Delete what we put down. 4, 5, 6, 7, 8, 9. Backtrack. 2, 3, 1, 2. And now we continue going. And what are we missing here? 4? Ah, too bad. So we will obviously have to backtrack and backtrack. And then, but we can see basically, hey, we need to backtrack to a 4 eventually over here, and then it will continue going on. So this is how the algorithm worked, where it basically just keeps going until it runs into a dead end and backtracks. This is a bit different. Now, this may feel a bit brute force, but actually brute force refers to an even worse tactic, which is that we would try combinations like this, where they're just invalid by default. Because brute force means try every single combination. Here, we're essentially, once we hit a dead end, we're pruning an entire huge amount of search space, right? If we hit a dead end over here, we know, oh, I shouldn't continue over here and continue with anything that's in this current configuration. Don't bother filling in any of these other spaces. So we're basically removing all possibilities of all those checks, which really does help optimize the amount of space we have to search. Otherwise, it'd be an unfathomably huge amount of space. So this is a very kind of worthwhile way to do things. So my advice for doing the Sudoku and this problem, once again, so 2 things. Once again, this position can be a int row or an int column. I'll go back to that in a second. The second thing is just make this basically return true when we're starting out. For Sudoku, you need to check the rows, you need to check the columns, and then you need to check your 3x3s. For the rows and the columns, and the 3x3s, I suggest like having your valid method call 3 additional methods. Or not, you can program them all in the valid method, but basically work on them independently. I will say checking your 3x3 grid, there's a number of ways to do that, but if you can't figure out a clever way to do it with math, you only need like 5 if-else statements to do it, 5 or 6 if-else statements, because there's 2 compound if statements and an else statement. That's it. If, else if, else if. 6 total, 1 for the row, 1 for the column. Okay, so, you can essentially brute force that check. But anyway, this position over here is very important. One of the common things I see for my Sudoku in my Sudoku puzzle is that is incorrect that I see students do. Is I see students do basically, okay, 4 int row. They basically don't pass in the int row. They do 4 int row, for int column, and then they do an if statement to check if row column is valid. If it's open, and then they try all that thing. In that case, you're searching for the next open space, but that means you don't know where you currently are. And if you don't know where you currently are and you're having to search for it, that can lead to some really unintentional behavior when it comes to backtracking. The point of this algorithm is that you always know where you are. Okay, you always know where you are. Last thing, extra credit is available on this assignment. It's 150 points, so about 50% more work than a standard problem, I'd say. 10 points for doing Project Euler 96, which is essentially the same. It is Sudoku, but here the way you do this after you solve your Sudoku puzzle. And what this does is that this gives you a text file that you just have to read and basically solve 50 puzzles. Basically, you get your file reading working, convert their format into whatever your format is, and then prove you solve the 50 puzzles by adding up this number over here. So this is 003 becomes 483, right? So you take 483, add that to the top left three-digit number of all the other solved puzzles. And then your sum basically ends up being in the 40,000s, and you can double check that. You can create an account to double check your correct answer that way. Basically, it just becomes an easy way to verify that you have solved all these puzzles. But yeah, it is very similar. It is very easy. It's an easy extension of this. Okay. So, any questions from the people on Zoom? So this is the way this is going to work. I'm going to try my best to pretend you people are actually here. And so if you have issues, speak. I'll check in occasionally and see. We can handle demoing later if you're behind on demoing, but you've turned in your assignments. As long as you've turned it in and they work, that's all I care about. Demoing can, if you're showing up, then I'm less strict about demoing. So just make sure those are turned in and stuff. Okay. So next, yes, I think it's due after spring break, the recursion. And I know a lot of students are still working on the maze, but I figured I'd give the opportunity just in case, I don't know, we get another snowstorm out of nowhere somehow and Thursday gets closed somehow. It's a mess. So I'd rather go over this video, and assuming everything's back to normal on Thursday, I'd rather spend Thursday being able to help people more one-on-one rather than explaining. So I just decided to do this explanation a bit earlier than I normally would. Okay. I'm going to go ahead and go around the room to help people. So I will stop recording here.